I write a simple compiler for a small imperative programming language called Elna. The compiler is written in itself, and because of it, it only uses the features that are already implemented, and we add new stages step by step, and each stage can do a bit more, understands more features, and can use these features. And today I will begin with a function that actually shouldn't exist. This is the copy operand function. It is called Elna RTL copy operand, and it shouldn't exist. It is a function from the RTL path, meaning register transfer language, and it converts 3-address code instruction into an RTL instruction. And this copy operand function, it assigns a TIC operand to a RTL operand as is, and this is actually wrong because RTL operands are just not the same as TIC operands, but it is done this way because I did not have an RTL path first, so I just copied the TIC path into additional path and modified it, and this was just a procedure that copies operand, by actually these operands are different things, and such copy is actually wrong. And I want to see where this thing is used at all. So copy operand, and the first case is, for example, this Elna RTL binary arithmetic. So it is a procedure that takes a TIC instruction that actually should have a different type. Its type actually should be Elna TIC instruction pointer. Okay. Elna RTL binary arithmetic. So it copies the first operand. The first operand of such an instruction is the target. So these two binary result operands are the operands of a binary expression, and this one is the result. Actually, we can rewrite this procedure a bit and just rename it later. Basically, this works this way, that some operands have the same order. So this is this Elna RTL kind, and for Elna RTL kind it is this register, immediate, symbol, and pseudo. I think that the copying makes sense only for immediate and symbols. For sure not for the list, and I think that pseudo variables are probably not the same for TIC and RTL. Pseudo registers. So here I check. No, pseudo registers are almost the same as the pseudo registers for the TIC. They are just converted to memory locations later but we can do it only during the RTL pass because it is the pass where I do stack allocation for a procedure. Well, at least what I want to say is that if I, for example, change the order in this enum, it will break the compiler because they cannot be assigned anymore. Exactly, we get an error because they cannot be assigned anymore since they do not have the same order as these TIC instructions. So we go to the OP operand once again, and here we just we get the operand kind and check it. If TIC instruction operands number kind is immediate, Elna TIC kind immediate, then it gets converted to an immediate value, and we just copy. Actually, we can do this assignment because we need to access these values more than one time. So we keep this assignments and just make the comparison a bit shorter. So we say that if operand type is immediate, and the difference is that we do not copy operand type as is, but we rewrite this as RTL kind immediate. And the same we can do for symbols, because symbols are global symbols. They are also the same. Let us see whether we need anything else. And I'm going to move the editing to the top half because I can see the screen better then. So here we look for this Elna RTL copy operand function, and here I go to the types, for example TIC kind. This is this one, and I would say let us try to compile it now. And it still fails. What could we need else? The pseudo registers probably. This is actually the last one that can matter, I think. Yes, that compiles. I do one final test. This command should also pass, and it works. And as I said, if I change the order of definitions, it shouldn't matter. Exactly, that compiles now, and even the final test that does comparison of the generated assembly with the previous stage, this test also passes. So that was it. Yeah, this is used, for example, for conditional jumps. This block can be rewritten, I think. Okay. Doesn't matter for now. So what can we do else? Then I have here this assign variable or assign pseudo register. So it is a pseudo register with a hard-coded name, and I have already a function that can generate the names automatically. So we can get rid of the hard-coded names, and it is the last name remaining. And we can get rid of it. So we have two if conditions here. Here we create a copy instruction, and probably we can just and this copy instruction is executed anyway. So let us just extract it and put to the top. Then we set the first operand of this instruction to the assignment. I only copied the first case, but haven't removed this one. And this thing is actually also done in both cases, and it is the same. And after that we set the operand of the current instruction, so of the previous thing, to the stuff returned by this. Oh, I see. I would overwrite the operand type here. So we get this operand type, operand value, and operand length from the TSC designator. And then we need to set the first argument, but in that case the second argument, to the returned values. So okay, we can keep it as this. If instruction isn't null, then concatenate them. Okay, but here we generate different instructions. Get address in one case, and there is the only case in the else branch. And LNTIC binary expression is called here as well. We could just use different variables for these things, probably. Okay, but this assigned variable is needed in any case. That actually means that on the top we can just generate a new variable. And here we use these operand type variables, but they are actually not the operand types, and they are assignee variables, and we are going to rename them, or I probably should create just new ones. Okay, let us copy them first and rename. And then we can assign I can assign them to the address on the left side of the assignment, and this one would be the length. And they are used in this role actually only here. type, value and length, and not the address but the value itself. So, and here they are reassigned anyway, and here you use the reassigned value, but here we use them again. So this is and here the same in the first case. I use the variables from the left side of the assignment, and after that they are redefined. So with a bit of luck it could actually compile. No, it doesn't. Who have fought this? Assigning. Okay. Oh, this line is too long. Definitely. Let us break it and try again. If I check the operand type here, I should of course check the assignee type. And in this case, I write the abstract syntax tree into the 3 address code. Okay. Now we can use this operand type value length things for the generated variable, but we can also, so this operand type, operand value, operand length are used now for the assignment, and I actually think that this binary expression visiting is probably done in each branch as well, because we always need to visit it, and we really do not have to do this 3 times. So let us also rename these 3, and we call them assignment type, assignment value, assignment value and assignment length. And we look for the operand type now, and I'm going to split the screen once again, and I will work in the top half of the screen. We call this assignment type, assignment value, and assignment length. Later, when we can pass more complex types on the stack, we can of course combine it in one struct. We can actually already do it. I do not need 3 variables each time. I cannot allocate aggregates on the stack yet, so I have to pass them one by one for now. So let us see where it is used else, and we check this assignment type, assignment value, and assignment length, and we do the same here, assignment type, assignment value, and assignment length, and here let us just copy them, and we can break the line here again, and we copy them in here and just remove the address sign, and the last case will be then here. So assignment and assignment. So we can assign them here. Is it correct? Yes, I think so. And that is, we check whether we broke something. I hope not. And one additional test. Okay, looks fine. And now we can use this operand type, operand value, operand length for the generated pseudo register. I should look how I called the function. It is called lntsc generate pseudo. So we can write here lntsc generate pseudo, and we pass the 3 variables. To this variable, and I actually should look where I use this assign statement, because I do not assign this pseudo variable to something. So how does the caller know where the result is saved? So it is used here. Here I use this variable once again. Probably, actually not, it is only an else case. So here in this else case I do not have this assign variable at all, and I have it twice here, probably just to save an intermediate result. But anyway, I will not need this variable then in each case. Okay, so let us just generate it there we need it, and operand type, operand value, and operand length. And we replace now this hard-coded variable with the generated one, and write here operand type, operand value, and operand length. And it can actually already be enough if we now replace also this case with the generated variable. We should of course replace the instruction and the operand number, and if I try to compile it now, then it compiles as it seems. So, and the second case would be the else branch, and here we can generate this variable and replace the hard-coded value with the generated pseudo register. So it is but it is operand type, operand value, type, operand value, and operand length. Exactly, and we also replaced the second case, so basically this one. It is actually almost the same thing. So let us compile it once again. And now we can see what functions we can move out of branches that are called everywhere. One of them is this LNTC designate procedure, but it is not the only one. So another one would be this binary expression that will be called everywhere. But what do I have between the designate expressions and binary expressions? So here I just set an operand on what? On this current instruction. Then I append it to the assignment instruction, and when I merge it with the instructions generated by the binary expression, and I append then the last instruction. I actually do not use these instructions anywhere else. I can just move it to the top and look how it is used everywhere else. So we also have the same thing here, and it is actually isn't used before, so we can just remove this assignment and set the operand the same as we do it here. And in the third case, this is also the same. We then do a check, so instruction isn't used before, but it is used after the assignment, so we can remove this as well. Since we were on the topic of the TIC operand, let us introduce here an additional kind. And this additional kind will be pseudo mem. We will use this one for the variables on the stack, for the aggregate variables like static arrays and records. And it would actually be interesting to see how they are handled currently. This current argument is actually an operand. I think I assign argument type, argument value, and argument length. So this is the value and length. It is a procedure call. And the second operand is a list of operands. Do I have a type that describes the TIC operand? Yes, I do. And these are these three values. So actually, I do not need to do this pointer arithmetic here. My current argument, I see. Or is it an array? This is probably an array of arguments. So my current argument in this case is just a pointer to an TIC operand. And that means that to access this thing, so current argument, and here I dereference it, which gives me the first field, but this is actually wrong, so we can access the kind to this operand. This should be the same. And we do not have to do this assignment With the pointer arithmetic, we can just move it to the next line and then assign the value here and assign the length here by accessing the field on the pointer. Okay, now we can combine these three statements in one. And this 12 is actually the size of a single element of this array, meaning it is the size of the NTIC operand, and this actually should compile as well. Okay. So here this is this case. This is register location, and here I saved directly a temporary variable counter in this symbol table or variable map as it's called here, and this is actually wrong because I cannot enter 0 here because it cannot be distinguished then from nil. So I cannot distinguish between a variable with an index with the counter 0 from a variable that just doesn't exist in the map when I do lookup. So I need to wrap this counter into some record and then save pointer to this record, so we always have an address at this place. And I'm thinking, how can I do it? So the thing that we save here is temporary variable counter. This kind of way is this allocation pass done. The allocation is done after the RTL generation, so these are actually I probably just going to give it a stupid name. Actually, the entries in this symbol table are called infos. For example, at least for the front-end symbol table, but here we have a different symbol table, and I will just call it RTL info because it is the RTL pass, and it is an entry in the symbol table. Let us see if I already have something similar. So we have kind, operand, instruction, registers. These are RISC-V registers. We do not have anything, so I just define a new record elna RTL info, and and I will do it here, but I will go to this variable map, allocate variable, exactly, and I always add 4 bytes to the counter, because I assume currently that all variables on the stack are 4 bytes long, and this restriction should be lifted later. So we defined this info object. We can call it counter, or we can call it offset, since it is actually an offset on the stack. Let us call it counter first. We can rename it later. And what we actually want to achieve is that we want to define a new variable. Let us call it ATL info, or the type pointer to the ATL info, and we have to allocate it only in this case. So we do a lookup. This is pseudo symbolic. This is already. Before I break the compiler, let me save the changes first, so that I can revert if needed before I break anything. That can happen. So we save our changes in this stage, and this variable becomes elna RTL info pointer, and we do a lookup. It will return a pointer to this info object. We check whether it is nil. If it is nil, we want to assign a value to it. So we allocate memory for this elna RTL info object, and to the counter member we assign so pseudo symbolic counter. We assign this temporary variable counter, and this pseudo symbol is then saved in the backend symbol table, pseudo symbol, and that's it. Actually, it won't work. This is expected. We need to look where this function is used and for what. So there are apparently far more than 2 places where it is used, and we start with the first one, be in here. Probably it will be the definition itself. Okay, so if this is an operation target and expected to be a register but is not register, then this procedure writes it to a temporary register and preserves its value in the following instruction. Okay, and here we allocate this variable, so pseudo symbol, and we need to assign it the correct type, being elna RTL info, and here we generate an instruction with the offset operand. so we get these offset. Then we go to the next usage. It is actually almost the same, only we use here this offset as an immediate value, so we can replace it with a counter, but we shouldn't forget to fix the type, otherwise the compiler cannot calculate the offset of the field. And this is in another case. So this pseudo variable is still elna RTL info pointer, and it is used in the offset operand again, so we can write here just counter. Just counter. RTL info pointer. So here we do the lookup, and it is still an offset instruction. Why all they look the same? They're probably just similar. And here RTL info, and pseudo symbol is used in the offset, in an offset, and that would be counter field. Is this the same function? Yes, this is the same function, and we access the counter. Pseudo symbol elna RTL info. Pseudo symbol. Okay. Undefined reference to symbol table lookup. Let us see what has changed. Is the second variable RTL info, and it isn't used anymore. Value length, the variable map is the global variable, so here we use this pseudo symbol, we allocate memory for it, assign the counter, then we do enter, change the global variable, and return this thing. This actually looks more or less fine. The one change that we can now do, we can reduce the size of the stack by 4 bytes. So actually, if I defined a procedure, for example, f, and I declare a variable, a stack variable, for example, of type word, and then I return this variable and we compile this stuff. Then if I look into the assembly, for this function f, then it will reference this. So this is prologue, and here begins the epilogue, and here we load the value x2 is the stack pointer. We load the value with the offset 4 from the beginning of the stack, and then we use 8 to store this value once again. Doesn't matter. This instruction should begin, and we load this once again into x10, which is probably a0. But we begin to use stack with the offset 4 and not with the stack with the offset 0 as it should be. So we create the stack that is 4 bytes bigger than it should be. Yeah, the stack size is wrong. I think that the stack should be a multiple of 32-bit at least, but it doesn't matter now. The thing that we do not use the offset 0 from the stack pointer. Actually, we have to look where this set the initial value for this variable counter, exactly variable, temporary variable counter. So here we just use it, but here we set, before we visit a procedure, we reset the variable map, because each procedure gets a fresh variable map, and we set the variable counter to 4. Somewhere I had a similar initialization code, but for what? For this pseudo counter. We can probably reset it there as well. Pseudo counter. Nine. Allocation would be too late for that. Okay. Then variable count, as I said, it can be 0 now, and then if we recompile that, yeah, then it uses 4 bytes less for the stack. So there were 20, now we allocate only 16 bytes. And the stack begins with 0 and not with 4. So that is fixed as well. These procedures aren't actually required anymore. I have to define them because I because I haven't used the ellipse first, but now we can just use the printf function for this stuff. So let us again save the current state. So we save the state 19. And now let us remove these two instructions just to see that they are used and that the compiler is broken if I remove them. Exactly. We can close the assembly file, and now we can replace them with a single printf thing, and we just write. So we need to write a string of special length. That can be done with the s, and I think this is the syntax, and the arguments go into in the reverse order, so first the length and now then the name. The string should be 0 terminated because it is a C function, and then we can compile it. That is fine, and now we can combine it with this stuff, so it can go after the is it a label name? Procedure, yeah, it is the procedure label. So then we generate the instructions, then we write the return statement. And that's it, I think. Now this is actually pretty the same thing. So we write this, we actually write that the label belongs to a function in the assembly, but it is actually almost the same. So we write procedure name and length. After this thing, we write then that this is a function instead of this semicolon, and there is some prefix to this thing. We say that the type of the procedure is this stuff, and I think that these three statements can be removed as well now. So we try to compile it again. Yeah, these two can be actually merged into one string. Right, C, right. And writes actually uses the printf write 0 terminated string, write character, and they had write s somewhere, I think. Yes, this one. Actually also pretty simple. Do we have write s somewhere? Yes, we have. Yeah, this case is actually this is the same, but here we write that our variable is not a function as in the previous case, but we say that it is an object. And let us actually replace it with the same. So we can just write printf here. Then we say that then we have the variable name, so it is a string with a given length, and then we write that it is an object, and we put a new line at the end, and the arguments are these two, but in the reverse order. So something like this should be actually fine. Then we write a label for the variable itself. And we write an initializer. So this is the type. Then we write the variable name. After the variable name we have a semicolon. Then we initialize it with zeros, so this can go. And after that we write the variable body, and body is just the size of the global variable. Write e actually just uses e, so we can then say that after 0 we write how many bytes we want to initialize, and that's it, I suppose. Then we have variable name, variable length, and at the end we write the new line, and that's it. So let us see whether this works. It doesn't. Space repeat count is 0. Looks like a warning. So what is wrong? Ooh. Okay, that looks better. That looks definitely better. Is write e used anywhere else? Write e. Yes, and also in this case we can just replace it with a printf right away. Probably I will replace them later with my own functions one day, but okay, for now it is easier just to use the printf. So we can actually just say printf, and when an integer, and integer is the counter, then this one can be removed, and write the count after that. And that's it. Okay, I see. We need to switch to buffered streams or to raw streams, but not use both of them because it is something error prone. And here said this is actually the same case. I can just remove this stuff and see what happens. And it still fails. And then we do it the other way around and just always write this dot or period. Then it compiles. So that would mean that this function is actually a printf, and after that count and length. So we can write counter of the given length, and it would be this. Then we need to terminate the string. And it fails, of course. It wasn't only the counter, it was a dot. But before the string, so here. Yeah. Length and counter. So we write dot, probably flush again. No. Okay, let us do it in steps. Then we write the count of the given length after the dot. So we just write this thing here, and we say that length is the first argument, and this can go then. And we need to flush the string probably after that. And we theoretically should be able to just put the dot here and to remove this line. Okay, that looks better. Do we need this flush call? Yes, we do. Can we have only one of them at the end? I would say it should be possible. Okay, and then rake passes auch. So where do we have right else? Here we write the register number, and this is actually the same. And we also do not need this procedure at all. Register, Elna, register. Yeah, well, we can probably later write more readable register names, but this generic X notation is enough for now. Let us write here print F as well, and then a null terminated, zero terminated string. Register -1 is the operand, and that's actually it, I think. Yeah, there are also cases where we just write integer. Write label. Yeah, I don't know. Write label doesn't seem to be very meaningful here. Let us move, put printf here, and we will just write dot and this stuff. The length comes in here, and we write a semicolon after that, and this one is replaced with a flash. Is already defined. Oh, so here it is sometimes the case as well, where that the value is nil, 0. So okay, we let it be as it is. But well, we reduced the number of the generated calls at some places, so that we can write some string with one function call instead of many. Okay, yeah, write C is used as well here and there, and I think I won't be able to improve it further. So today we changed just a few things, so mostly it were just improvements here and there. Here and there we replaced the hard-coded pseudo registers with the generated ones and improved the stack location, so that procedure stack takes less storage, and we just improved some functions calls and reduced some code in the compiler so that we can do some things shorter. And I will continue to work on the compiler next time then.